For our last video in our first chapter, we are going to come back to the special case of Lewis structures where we have resonance. We're going to do a brief introduction, we're going to talk about the rules and the reality, and then we'll look at how to draw the resonance structures and how to draw the resonance hybrid. Early in this chapter, as we were drawing Lewis structures, we came across the example of carbonate, and we saw that we could actually draw three different Lewis structures. So we have the carbon in the middle connected to three oxygens, and this could be a double bond with two lone pairs on the oxygen, three lone pairs on this oxygen and a negative formal charge, three lone pairs on this oxygen and a negative formal charge. Or we could have the double bond here, or we could have the double bond here. Now, looking at these Lewis structures, here we have a carbon-oxygen double bond, and here we have carbon-oxygen single bonds. So these Lewis structures suggest that the carbon-oxygen bond lengths are going to be different. We would expect to have a short C double bond O and a longer C single bond O. But experimentally, it's been shown that all of the carbon-oxygen bond lengths in carbonate are the same. All of the CO bond lengths in carbonate are the same. So what this tells us is that this is not an adequate representation of what actually exists. So what we need to account for is the fact that rather than having this pair of electrons localized between this carbon and this oxygen, instead, these electrons are delocalized and spread out among the different CO bonds. So what actually exists then, we need to consider the resonance hybrid. So our carbon is connected to three oxygens by a single bond, but there is also partial double bond character between each carbon and oxygen. We have a partial negative charge on each oxygen as well. So the resonance hybrid then is kind of an average of the different resonance contributors. So we represent the fact that these are resonance contributors using a resonance arrow. And this is our way of representing the fact that each of these Lewis structures, although it's a valid Lewis structure, it does not adequately reflect what's known experimentally about this compound. So we draw the resonance arrow, which tells us that this is a resonance contributor or a resonance structure or a resonance form. Different terms could be used. This is in resonance with this form, and this is in resonance with this form as well. None of these exist. That's another very important thing to keep in mind. If we were able to take a snapshot, we would not see some molecules existing like this, and some like this. Instead, what exists is the hybrid. Every single molecule would exist as the hybrid, where we have equal bond lengths between the carbons and the oxygens. We have partial negative charge on each oxygen. So resonance is the delocalization of electrons. And this delocalization of electrons leads to a special stability. We can think about the fact that when electrons are delocalized, that means that they are attracted to multiple nuclei, so that offers some stability. Also, if we have a charge in our species, then having that charge spread out over multiple atoms rather than concentrated on a single atom, that makes it more stable as well. One thing that is required for resonance is the presence of p orbitals, because the delocalization occurs through a pi system. So the delocalization of electrons occurs through a pi system. Now, some of the features that we need to keep in mind are that resonance structures, the resonance contributors, resonance forms, these are all imaginary. The movement of electrons that we use to interconvert between different resonance structures, these are also imaginary. We need to use the Lewis structures, the resonance structures, to be able to keep track of how many electrons we have, what kind of bonds we have, but each structure does not exist. We also have to remember that resonance forms differ only in the placement of electrons. If we have a hydrogen in a different place, then we're not talking about resonance structures, we're talking about isomers. So resonance forms differ only in the placement of electrons. Resonance forms are not necessarily equivalent to each other. On the previous slide, when we were looking at carbonate, in each resonance structure, we had one double bond between carbon and oxygen, two single bonds between carbon and oxygen. We had two negative charges, right? Those were equivalent, but that is not always the case. Resonance forms must obey the rules of valency. So even though the structure doesn't actually exist, we still have to draw a valid Lewis structure. We can't have something with 5 bonds to carbon, for example. We must have a valid Lewis structure. And another feature is that the resonance hybrid is more stable than any individual forms if they were to exist. So there is an advantage to the molecule to exist as the resonance hybrid rather than existing as any of the individual resonance structures. How do we know when resonance structures are possible? Well, we have to be on the lookout for the presence of a pi system. In other words, we might have a carbon-carbon double bond. That would be one example where it might be possible to have resonance structures, because there is the possibility of delocalizing the electrons within the pi system. We might also have lone pairs of electrons adjacent to a pi bond, and we're going to see some other examples. Now, how do we go about drawing resonance structures? When we are converting one resonance structure to another, we are only moving electrons. Notice I have movement in quotes because we are talking about the imaginary movement of electrons. Furthermore, each resonance structure must be a valid Lewis structure. So even though that Lewis structure doesn't exist, it still has to follow the rules for valid Lewis structures. And it's also important to keep in mind that equivalent resonance structures will contribute equally to the hybrid, whereas for non-equivalent resonance structures, the more stable structure would contribute more to the hybrid. Well, I just told you that these structures don't actually exist, so how do we know which one is more stable if it doesn't exist? So, there are some issues here, and we have to imagine the relative stability of different resonance contributors. If everybody has an octet, that's going to be more stable than if any atom doesn't have an octet. If we have a negative charge on a more electronegative element, that's more stable than having a negative charge on a less electronegative element. So there are a number of features like this that we use to evaluate, even though we are evaluating something that doesn't exist. Let's take a look at how we would draw the different resonance structures, starting with carbonate. So if this was the structure that we started with, how should we look at this and try to figure out whether we can draw additional resonance structures? Well, we have a double bond, so that means that we have at least one pi bond, so we have a pi system. Now, what about these oxygens? We just talked about hybridization, and if we are looking at this oxygen, this is connected to one lone pair, two lone pairs, three lone pairs, and a bond. This is connected to 4 groups, so we would predict that it would be sp3 hybridized. However, it is possible that instead this would take on sp2 hybridization, which then means that there is a p orbital which could be involved in the delocalization of electrons. So even though we would look at these oxygens and at first glance we might assume that they are sp3 hybridized, there will be more stability if they are sp2 hybridized, which gives us p orbitals, which gives us an extended pi system. Now, for this one in particular, because we are starting out with lone pairs and a negative charge, it is helpful as we're trying to draw additional resonance structures, it's helpful to start with one of these lone pairs and then imagine these electrons are moving away. Now, we also just talked about using curved arrows to represent the movement of electrons. So if we are moving a pair of electrons, it would look like this. In the case of resonance structures, we're talking about the imaginary movement of electrons. So I prefer to use an arrow like this. I want to have a dotted line. This is only my approach. Textbooks don't use this, so be aware of it when you're looking at other resources. But because we're talking about the imaginary movement of electrons, I want to represent it like this. So imagine we are starting with this pair of electrons, and now imagine these move here, and then that pushes these electrons up here. So that will give us another resonance contributor that looks like this. We now show a double bond here, single bond here, extra lone pair up here, and now the negative charge is on this oxygen. If we imagine that one of these pairs of electrons move in, that is going to move these out, which brings us right back to this one. So an alternative is that one of these pairs of electrons move here to form a double bond, pushing these electrons back onto this oxygen, giving us a double bond here. We still have these two lone pairs. This is now a single bond, negative charge. This is still a single bond and a negative charge. So thinking about starting at an atom that has a negative formal charge and taking those electrons and moving them away, that enables us to draw the different resonance structures. For this example, because all three of these are equivalent resonance structures, they will contribute equally to the hybrid, and so the resonance hybrid would just be the average of all three of them. So I'm going to draw the resonance hybrid up here. We have a carbon, oxygen, oxygen, oxygen. We have partial double bond character here, partial double bond character here, and partial double bond character here. So we could call this a partial minus, partial minus, partial minus, where that is a delta for partial. Or if you notice that this oxygen has a negative charge in 2 out of the 3 resonance contributors, we could alternatively label this as negative 2/3, negative 2/3, and negative 2/3. So you might see it in either way. Let's look at a few more examples of how to draw resonance contributors and the resonance hybrid. So our next compound here, C6H6, this is called benzene. So this exists as a 6-membered ring, and we can draw this with alternating single bond, double bond. Each carbon is connected to a hydrogen, and each carbon is sp2 hybridized, which then gives us a p orbital, which gives us the pi system that's necessary for resonance. From this representation of benzene, we can draw another resonance structure where we imagine that these electrons move here, as these electrons move here, as these electrons move here, giving us another resonance contributor where we now have our double bond here, and double bond here. Experimentally, it's been shown that all of the carbon-carbon bond lengths in benzene are the same length. So they do not exist as a short double bond and a longer single bond, but instead they exist as the hybrid. Therefore, to draw the hybrid, we would have all single bonds between our different carbons, and then we also have partial double bond character all the way around the ring. Both of these resonance structures are equivalent to each other, and so they would contribute equally to the hybrid. Recall in the example on the previous slide with carbonate, because we started with an atom that had a negative charge. Those were the electrons that I moved first, moving away from the atom. We don't have a charge here, we don't have a charge here, so you can just pick a bond and imagine that those electrons move. But remember that because we have a hydrogen here, if I moved these electrons here, giving us a double bond, that would give us 5 bonds to carbon. So if these electrons move, these electrons also have to move away, and these electrons have to move away. Now here we have another example where we have an anion. So if we start with this structure, we have a CH3 connected to a C double bond O connected to a CH2, where this carbon must have a lone pair and a negative formal charge. Now we have a double bond here. This carbon must take on sp2 hybridization, which gives us electrons in a p orbital so that we have a pi system. Now we can draw another resonance structure where we imagine that these electrons move here between the carbons, pushing these electrons up here onto the oxygen. Now, once again, because we started with a negative charge on this carbon, then it's easiest to draw another resonance structure by imagining moving these electrons away from the carbon with the negative rather than trying to move electrons toward the negative. So after this imaginary movement of electrons, we have our CH3 hasn't changed. This is now a carbon single bonded to oxygen, and that has a negative formal charge. And here we have a double bond between the two carbons. Unlike the examples with carbonate and benzene, these two resonance structures are not equivalent to each other. So this is where we need to evaluate their relative stability if they were to exist. Now we have the same number of bonds, so there's not a difference that way. We have the same number of charges, so there's not a difference that way. The only difference is about who has the negative charge. Here we have carbon with a negative formal charge. Here we have oxygen with a negative formal charge. Because oxygen is more electronegative, that means oxygen will be happier with a negative charge compared to carbon. So this one will be the major resonance contributor. So when we think about our resonance hybrid, we could imagine then that our resonance hybrid is going to look more like the starred resonance structure. So we're going to have significant double bond character here and just a little bit of double bond character here. We're going to have a small partial negative, and here we're going to have a big partial negative. Right? So our resonance structure is going to be kind of a weighted average between these two, where this one is weighted more heavily. And so our resonance hybrid is going to look more like this one. Now let's look at a few more examples. Here we have CH2. This must be double bonded to a CH, which is single bonded to a CH2. Because this carbon has a negative charge, then there must be a lone pair of electrons, which gives this carbon a negative formal charge. Now we can imagine that these electrons move away from this carbon, which will push these electrons onto this carbon, giving us another resonance contributor. This is now a single bond. This is now a double bond. Here is the lone pair, and now this carbon is the one that has the negative formal charge. So the resonance hybrid, we've got our CH2, CH, CH2, partial double bond character here, partial double bond character here, partial negative, and a partial negative. In our next example, once again, we have our CH2, which must be double bonded to a CH, which is single bonded to a CH2, and now this carbon must have a positive formal charge because it only has 3 bonds. Now up here, we started with our extra electrons and then we moved away, but here we don't have extra electrons. So instead, we want to move toward a positive charge. So imagine moving our electrons toward the positive charge. So these electrons are going to move over this way. And that is going to give us another resonance structure. This is now a single bond, and now this is a double bond, and then this carbon is the one that has the positive formal charge. In this case, our hybrid, it is the average of the two because the two resonance contributors contribute equally. So this one has a partial plus, and this one has a partial plus, partial double bond character. Now, in our third example, we have a radical. So this is a CH2 double bonded to CH, single bonded to a CH2, and here we have a radical, which is an unpaired electron. And unlike the examples above where we moved a pair of electrons, in this case, we're going to move single electrons. So we'll be using our single barbed arrow rather than our double barbed arrow. But another difference, if we think about these electrons, we're moving kind of in the same direction. So it's like we're moving downstream. But with radicals, because we're moving single electrons, it's going to look different. So let's imagine that this electron moves here toward the bond, and then out of this pair of electrons, one of them is going to come back here to serve as the second electron of that bond, and then the other electron that was part of this original covalent bond is going to move on to the carbon. So that gives us, we still have our CH2. This is now a single bond to CH, double bond to CH2, and here we have our unpaired electron. So this bond was originally present, but this bond consists of what used to be this electron and one of these electrons. What used to be this bond is now one of them is over here and the other one is here on the carbon. Our resonance hybrid, we have our CH2, CH, CH2, partial double bond character, partial double bond character. Now we don't kind of have the same practice of having a partial negative, partial positive. If you want, you can write this as a partial radical. I'm okay with that. There isn't really a rule for it. So something like this would be okay. All right, so in terms of trying to draw resonance structures, if you're starting with a negative, then it's great to imagine moving away. If you have a positive charge, then a starting point would be to imagine moving the electrons toward that positive. And if you have an unpaired electron, well, just move away and towards that unpaired electron. Another thing that I want to point out, this is very important, is to keep in mind that whether we are talking about the movement of electrons or the imaginary movement of electrons, we are always talking about using curved arrows to represent the movement of electrons. We never, ever, ever draw arrows to or from charge. This carbon here started out with 1, 2, 3 bonds, so it owns 3 electrons, and it owns this lone pair, so it owns 5 electrons, which gives it a formal charge of -1. In the end, this carbon now has 1, 2, 3, 4 bonds, so it owns 4 electrons, giving it a formal charge of 0. This carbon now owns 1, 2, 3 electrons from those 3 bonds. It owns this pair of electrons, so it owns 5 electrons, giving this a formal charge of -1. So we want to think about moving electrons using the arrows to show the movement of electrons, and then the charge results. Okay, we are not drawing an arrow to or from the negative charge. We do not draw an arrow representing this positive charge moving over here. After these electrons have moved, now we look at this carbon and we see it only has 3 bonds, so it only owns 3 electrons, which results in a formal charge of a +1. So We're using the curved arrows or the dotted curved arrows to represent the movement or the imaginary movement of electrons, and then the formal charge is what results. So now that we've seen a few examples, it's important for you to continue to practice so that you can become more familiar with drawing resonance structures, drawing the resonance hybrid, and overall having a better understanding of organic structures.